Welcome to Section 2, Data Understanding. In this section, we shift our focus to understanding the data that will drive our analysis. Before we can prepare data, build models, or evaluate performance, we must first take time to explore and understand what data we have and what data we still need. In the CRISP DM process, data understanding represents the critical bridge between business objectives and analytical work. After identifying what the business needs, our next question becomes, what data will help us solve this problem? In this phase, we begin by collecting the initial datasets, examining their structure, and exploring their basic characteristics. We look at data types, formats, and sources, and begin forming a first impression of data quality. Are there missing values? Are there unusual patterns or outliers? Are the variables we collected sufficient to answer the research question? Data understanding also involves developing intuition about how different variables relate to one another. Through summary statistics, visual exploration, and basic pattern recognition, we start discovering meaningful insights, even before formal modeling begins. Ultimately, the purpose of this phase is to build a clear and confident foundation for all the steps that follow. By fully understanding our data from the start, we ensure that our later modeling work is accurate, relevant, and aligned with the business objective. In this section, we will learn how to explore, describe, and evaluate data effectively so that we can move forward with clarity. The first stage of our data understanding process is initial data collection. In this step, our main objective is to gather all datasets required for the project or ensure that we have proper permission and access to them. This is the foundation for everything that follows. At this stage, we identify where the data comes from, download or access it, and load it into the analytical environment, whether that's Python, Google Colab, Excel, or another tool. Once the data is loaded, we often notice early issues such as formatting problems, encoding inconsistencies, or missing values. These observations mark the beginning of data preparation. The main output of this stage is an initial data collection report. This report must clearly list all datasets obtained, where they are stored, and how they can be accessed. It should also describe any challenges encountered during the collection process and how they were resolved. This documentation ensures that the project is transparent, reproducible, and useful for future researchers who may work with the same resources. In summary, Stage 1 lays the groundwork by ensuring that all required data is properly collected, organized, and ready for deeper exploration. Python provides several ways to read data from different sources, but the most commonly used tool in data analysis is the Pandas library. Pandas is designed to help us work with datasets easily and efficiently. It allows us to load data from many file types, including CSV, Excel, JSON, and even SQL databases. Once the data is loaded, Pandas provides simple commands to view summaries, inspect the structure, and check basic statistics. As PD is a way to alias the Pandas library, making it easier and quicker to use throughout your code. Because Pandas can quickly convert raw data into a clean and organized format, it has become an essential tool in every analytical workflow. Throughout this course, we will use Pandas frequently to load, explore, and prepare data for further analysis. Here, we can insert a dataset like a CSV or Excel file into Google Colab. Let's use the Boston housing dataset from our course files. You can find the file on Canvas File Datasets. This dataset is a classic used in both statistics and machine learning. Each row represents one neighborhood in Boston, and each column represents a specific characteristic, such as housing prices, population levels, or socioeconomic factors. Click Upload to Session Storage on the top left. Choose the file you want to insert, then click Open. The field will be dismissed every time you close the Colab. You have to upload the file every time. Then we can use Panda's read CSV function to pull the dataset. Also, we can use header function to display the top 5 rows of the dataset just to check how dataset looks like. This dataset is a great example of rectangular data. Rectangular data means the information is stored in a two-dimensional table. Rows represent individual records or observations. Columns represent features or variables. This format is widely used in data analysis because it is simple, organized, and compatible with tools like Excel, SQL, Python, and especially Pandas. With this structure, we can easily filter, sort, visualize, and analyze the data to gain insights. After we load data using the Pandas library, the result is called a data frame. A data frame is a two-dimensional table made up of rows and columns, very similar to an Excel sheet or a table in a database. Each column can store a different type of data, such as numbers, text, or dates. Because of this flexible structure, data frames make it easy to select, filter, sort, summarize, and visualize data. They are one of the most important tools in data analysis because they help us quickly organize and explore datasets clearly and efficiently. Now we can finish the initial data collection report for the Boston dataset. The dataset that is acquired is Boston, which was provided by the lecturer. The method used was to upload the file to Colab, then read the file using Pandas. There is no problem while collecting the initial data. Now that we have collected our dataset, the next step is to take a closer look at what the data actually contains. In this stage, our goal is to examine the surface characteristics of the dataset and develop an initial understanding of its structure. We begin by checking basic properties such as the data format, the number of records or rows, the number of fields or columns, and the names of those fields. These details help us understand what information the dataset provides and how it is organized. To document this process, we create a data description report. And this report summarizes the type of data we obtained, the size of the dataset, the meaning of each variable, and any early patterns or irregularities we notice, such as unusual values, empty fields, or unclear labels. The report also evaluates whether the available data is suitable for the project's goals. We can use shape attributes to find out how many rows and columns are in a table. We can use info method to get an overview of the dataset, including the missing value and data type of each feature. Now we can continue the initial data collection report for the Boston dataset to make it as part of the data understanding report. As there are 14 features which are columns and 506 records, so far there is no missing value. Now that we have collected and described our dataset, the next step is to explore the data to build an initial understanding of its characteristics. In this stage, our goal is to start answering basic data mining questions using simple queries, visualizations, and summary statistics. We begin by looking at the data type, following by exploring the distribution of key variables, especially the target variable if our project involves prediction. We'll also examine relationships between different fields, for example, checking correlations or creating simple charts to see how variables interact. This process helps us discover patterns, trends, and meaningful groups within the data. And the output of this step is a data exploration report. And this report summarizes our early findings, highlights interesting patterns, and identifies issues or opportunities that may influence the next step of the project. We may also include visualizations to clearly show any trends or insights that should be investigated further. In statistics, data is generally divided into two major categories: quantitative and qualitative. First, quantitative data, also called numerical data, represents measurable quantities such as height, weight, price, or age. Quantitative data can be discrete or continuous. Discrete data includes values that can only be whole numbers, such as the number of students or the number of cars. Continuous data can take any value within a range, such as temperature or time, and is usually measured rather than counted. Next, we have qualitative data, also called categorical data. Qualitative data describes characteristics or categories such as gender, occupation, hometown, or product type. These values cannot be used for direct mathematical calculations. Qualitative data can be further divided into nominal and ordinal types. Nominal data consists of labels with no natural order, for example, colors, brands, or types of fruits. Ordinal data represents categories that follow a meaningful order, such as satisfaction levels from poor to excellent, or class levels like freshman, sophomore, and junior. Understanding these data types is essential because they determine which statistical methods and visualizations are appropriate for analysis. In both Python programming and statistics, data types are essential because they define the nature of the data, determine what operations can be performed, and guide how the data should be interpreted. While Python has specific data types for programming purposes, these often correlate with the types used in statistics. For example, in Python, the numeric data type has two main types: int for whole numbers, like 120 or -5, and float for real numbers with decimals, such as 1.5 or -2.7. These map to two statistical concepts: discrete data, which represents countable quantities, often whole numbers like the number of students, and continuous data, which represents measurable quantities that can take any value in a range, such as height or temperature. Next, we have categorical data types. The base Python type is string, used for textual data such as apple or mail. If you're using the pandas library, you'll also see the category type, which is an efficient way to store categorical variables with limited possible values. Statistically, these break down into nominal data, categories without a meaningful order like gender or color, and ordinal data, categories with a meaningful order but without measurable difference, such as rankings or grade levels. Now, a crucial point. Python types and statistical types are not always perfectly matched. For instance, a column might be a Python integer, but the numbers like 335 or 372 representing different course names, or 1, 2, and 3 representing different group IDs are actually categorical data in a statistical sense. We must always understand the meaning of the column to determine its correct statistical type. In this section, we begin exploring quantitative data by understanding estimates of location or measures of central tendency. The first and most common measure is the mean, also known as the average. The mean represents the balance point of a dataset. We calculate it by adding all values together and dividing by the total number of observations. For example, with the values 3, 5, 1, and 2, the mean is 11 divided by 4, which equals 2.75. In statistics, we often use the symbol X bar to represent the sample mean. In Python, the mean of all numeric columns can be calculated using the mean method in a pandas data frame. We can also compute the mean of a single column by selecting that column and applying the mean method. Sometimes, extreme values can pull the mean too far in one direction. To reduce the influence of outliers, we can use the trimmed mean. A trimmed mean works by removing a fixed number of the smallest and largest values, and then calculating the average of the remaining data. This approach is commonly used in competitive scoring systems. For example, in gymnastics or diving, the highest and lowest judges' scores are removed to prevent bias, and the final score is the average of the middle values. In Python, we can calculate the trimmed mean using the trim_mean function from scipstats. We simply choose the column we want to analyze and specify the percentage of values to trim from each end. For example, this coding means trimming 10% from both ends of a column removes extreme values and produces a more stable estimate of the center. The median is another important estimate of the location. Unlike the mean, which uses all values, the median depends only on the middle of a sorted dataset. If the dataset has an odd number of values, the median is simply the middle value. If it has an even number of values, the median is the average of the two middle values. Because the median is not affected by extreme values, it can give a more accurate picture of a typical observation. For example, in extremely wealthy neighborhoods, a few very high incomes can raise the mean dramatically, but the median remains stable and continues to reflect the income of an ordinary household. In Python, calculating the median is straightforward using the median method in pandas. Together, the mean, trimmed mean, and median help us understand the general location of numeric data and provide essential insights into the structure of a dataset. Now let's see an example. The table state shows the first few rows in the dataset containing population and murder rates for each US state. Let's see how to compute the mean, trimmed mean, and median for the population feature using Python. Firstly of all, you need to download the state table from Canvas and drag it into the Colab. Use pandas to read the state dataset. Then we can print the mean, trimmed mean, and median. Here, since we imported the trimmed package before, we don't need to import it again. If you don't import the required package, don't forget to import it as necessary. Now, we continue our exploration of descriptive statistics by focusing on variability, a key concept that helps us understand how spread out or consistent our data is. We will look at two major ways to measure variability: the standard deviation and percentile-based measures. One important way to describe variability is through the deviation, which is the difference between an estimate of location and the observed data values using xi minus x bar. Deviation tells us how far data values typically fall from the mean. Then we can compute the variance, which is the average of the squared deviations from the mean. Because variance uses squared values, we take the square root to return to the original scale. This gives us the standard deviation. The standard deviation is widely used because it is easy to interpret and works well in statistical modeling. In Python, we can calculate it with the std method in a data frame. Understanding standard deviation helps us judge whether our data is tightly clustered or widely spread. This example shows how to use standard deviation to represent the variability of the number of students in a class around the mean class size. We can tell from the second column that the mean class size is 44. Then we calculate the deviation about the mean using xi minus x bar. This step shows how far each individual class size is from the average size. For example, the class with 54 students has a deviation of 10, and for the class with 32 students, the deviation is negative 12. The next step is to square each deviation to eliminate negative signs. This is the value used to measure overall variability. The squared deviations are 4, 100, 4, 4, and 144. At last, we calculate the sum of squared deviations. This sum is the numerator used in the calculation of variance and subsequently the standard deviation. The standard deviation, STD, is the final result of this process and provides a measure of how much the data typically deviates from the mean. We can firstly divide the sum of squared deviations by the number of observations, which is 256 divided by 4, that is 64. Then we take the square root of the variance, which is 8. Another way to measure variability is to look at the spread of the sorted data using percentiles, also known as order statistics. The simplest measure is the range, which is the difference between the maximum and the minimum. But because the range is sensitive to outliers, we often use percentile difference instead. The most common example is the interquartile range, or IQR, which is the difference between the 75th percentile and the 25th percentile. The IQR shows the spread of the middle 50% of the data and is much more robust to outliers. In Python, we can compute percentiles using the quantile method and find the IQR with quantile 0.75 minus quantile 0.25. Together, these percentile-based measures help us understand variability even when extreme values are present. One important way to understand how data is distributed is by using percentiles. Percentiles divide the data into equal parts and show the values below which a certain percentage of observations fall. For example, quartiles represent the 25th, 50th, and 75th percentiles. This gives us a quick snapshot of the spread of the data. In Python, we can calculate percentiles using the quantile method in pandas by simply passing the list of desired percentiles. Large gaps between percentiles tell us the data varies widely. Box plots are visual tools built from percentiles. They show the median, quartiles, spread, and possible outliers all in a single plot. In pandas, creating a box plot is simple using the plotbox function, and additional labels can be added through matplotlib. Box plots help us quickly identify patterns, skewness, and unusual values. Another useful way to explore a variable is by looking at how often values fall within different intervals. A frequency table divides the full range of a variable into equally sized bins and counts how many values fall into each bin. In Python, we can create these bins using the cut function, and then use value counts to build the frequency table. A histogram is the visual version of that frequency table. Each bar represents a bin, and the height of the bar shows how many observations are in that interval. Pandas provides an easy way to create histograms using a plot histogram, where we can also define the number of bins. Histograms are helpful for spotting skewness, modality, and empty regions in the data distribution. A density plot provides a smooth, continuous curve that represents the distribution of a variable. It can be thought of as a smoothed version of a histogram. Unlike histograms, which have abrupt jumps between bins, density plots reveal overall patterns more clearly. In pandas, we can generate a density plot easily using the density method. We often create a histogram first, set density equal sign true to normalize it, and then overlay a density curve on the same axis. Density plots are especially useful when comparing different distributions or when we want a more refined view of how values are concentrated across the range. Now, let's explore how to summarize categorical variables, especially those with only a few categories. We will look at how frequency proportions help us understand patterns in the data and how bar charts provide a clear and effective visual summary. For example, consider flight delay data at Dallas-Fort Worth Airport. Since 2010, delay causes have been grouped into categories such as airline-controlled delays, air traffic control delays, weather delays, security issues, and late inbound aircraft. By calculating the percentage of flights in each category, analysts can immediately see which factors contribute most to delays and identify patterns that may require deeper investigation. One of the most common ways to display categorical data is the bar chart. In a bar chart, categories appear along the x-axis, and the y-axis shows either the frequencies or proportions. In pandas, we can easily create a bar chart after computing the frequency counts for a categorical variable. For example, using the wage.csv dataset, we can visualize the marital variable by first calculating its frequency and then using the plot bar function. Although bar charts look similar to histograms, they serve different purposes. Histograms display numeric data divided into continuous intervals and their bars touch. Bar charts display independent categories and therefore the bars are separated. Bar charts give us a simple but powerful way to compare categories and understand how the data is distributed. The mode is the value that appears most frequently in a dataset. In cases where multiple values occur with the same highest frequency, all of them are considered modes. For example, the mode of the causes of delay at the Dallas-Fort Worth Airport is inbound, since this category occurs more often than the others. Another example is marital status data, where married is the most common category and therefore represents the mode. The mode is typically used as a summary statistic for categorical variables, and it is generally not applied to numerical data because frequency patterns in numeric values often do not provide meaningful insights. Another important idea in statistics is probability. Probability describes the chance that an event will occur based on the proportion of times it would happen if we could repeat the situation endlessly. When we work with categorical data, we often summarize it using proportions, and a common way to visualize these proportions is with a bar chart. Categories might represent groups such as apples versus oranges, levels such as low, medium, and high, or even numeric data that has been grouped into bins. Although frequency and probability are related, they are not the same. Frequency tells us how often an event occurred in the data. Probability tells us how likely it is to occur. For example, in a marital status dataset, the category married appears 2,074 times. By itself, this number doesn't mean much. But if we convert it into a probability, 0.691 comma or 69.1%, we can clearly see that married is the most common category. To visualize these probabilities, we can create a bar chart and set the parameter normalized equal sign true. This converts raw counts into relative frequencies, allowing us to see each category's probability directly. This makes bar charts a powerful tool for interpreting categorical distributions. Sometimes, categorical data represent outcomes that can be mapped to meaningful numerical values. For example, imagine a cloud service company offering two subscription plans, one priced at $300 per month and another priced at $50 per month. To generate leads, the company hosts free webinars. Based on historical data, they estimate that 5% of attendees will subscribe to the $300 plan, 15% will subscribe to the $50 plan, and the remaining 80% will not subscribe at all. To summarize the financial potential of each attendee, we calculate the expected value, which is a weighted mean where the weights are probabilities. We multiply each outcome by the probability of that outcome and then add the results. For this example, the expected monthly value per attendee is 0.05 times 300 plus 0.15 times 50 plus 0.8 times 0, giving us an expected value of $22.50. Expected value is widely used in business forecasting, valuation, and capital budgeting because it incorporates uncertainty and future expectations into a single, interpretable number. Now it is time to focus on exploring relationships between quantitative variables. In many data science or research projects, exploratory data analysis begins by examining how variables relate to one another. This includes studying correlations among predictors and between predictors and a target variable. As we discussed in Section 1, the goal of statistics is often to find a simple, interpretable model that explains how input variables, also called features, are related to an outcome variable or target. When we look at two quantitative variables, x and y, we often want to know whether they move together. If high values of x tend to occur with high values of y, we call this a positive correlation. If high values of x tend to occur with low values of y, we call this a negative correlation. Understanding these relationships helps us identify meaningful patterns and informs the development of predictive models. To measure how strongly two numeric variables are associated, we use Pearson's correlation coefficient, which ranges from -1 to +1. A value near +1 indicates a strong positive relationship. A value near -1 indicates a strong negative relationship. And values near 0 suggest little or no linear relationship. To compute Pearson correlation, we multiply the deviations from the mean for variable 1 with the deviations from the mean for variable 2, then divide by the product of their standard deviations. In pandas, the core function makes this very easy. It computes pairwise correlations between all numeric columns in a data frame. The results are often shown as a correlation matrix, which is a table that summarizes every pairwise relationship. This matrix is a key tool in understanding which predictors may influence the target variable and whether some predictors are redundant due to high correlation. To better visualize correlations across many variables, we can use a heat map. In Python, the Seaborn heat map function provides a clear and intuitive way to see correlation strength and direction. First, we imported the Seaborn library. Seaborn is built on top of matplotlib and is especially good at creating statistical visualizations like heat maps. Inside the heat map, we pass data core. Data is a pandas data frame. Core computes the correlation coefficient between every pair of numerical columns. Now we draw the heat map. Value min and value max define the minimum and maximum values of the color scale. Since correlation values always fall between -1 and 1, setting these ensures colors are consistent, and different heat maps are easier to compare. This creates a diverging color palette. One color represents negative correlations, another represents positive correlations, the middle color represents zero correlation. Using a diverging palette is ideal for correlation matrices because it visually separates positive versus negative relationships. The colors tell the story. Dark blue represents strong positive correlations close to +1. Dark red represents strong negative correlations close to -1. Light colors indicate weak or no meaningful relationships. The diagonal of the heat map is always 1 because each variable is perfectly correlated with itself. By examining a heat map, we can quickly identify key relationships. For example, in the Boston housing dataset, a strong negative relationship often appears between LSTAT, the percentage of lower status population, and MEDV, the median value of homes. And this means that neighborhoods with higher LSTAT values tend to have lower home prices. Heat maps help analysts spot patterns, select useful predictors, and understand the structure of the dataset, which are essential steps before building statistical or machine learning models. The standard way to visualize the relationship between two measured data variables is with a scatter plot. The x-axis represents one variable and the y-axis another, and each point on the graph is a record. We can use plot scatter method to create a scatter plot in Python between two quantitative variables. X equals to log wage sets the horizontal axis to the log wage column. Y equals to wage sets the vertical axis to the wage column. Each dot represents one observation in the dataset. The marker sets the shape of each point in the scatter plot. It is the Unicode character for a circle. The plot is assigned to the variable x, which is a matplotlib axis object. This allows you to further customize the plot later, such as adding titles and changing labels. The returns have a positive relationship. Now, we explore how to summarize the relationship between two categorical variables. A common tool for this is a contingency table, which shows the counts for every combination of categories. Here is an example from Lending Club data, where loans are assigned a grade from A to G, and each loan has an outcome such as fully paid, current, late, or charged off. This contingency table helps us quickly see how often each grade appears with each loan outcome. It provides a structured way to examine whether the categories of one variable are associated with categories of another. In Python, we can easily create a contingency table using the crosstab function. We set index to the loan grade, which forms the rows, columns to the loan status, which becomes the columns, and margins equal sign true, which adds row and column totals. We can also convert the table into percentages instead of counts by adding the argument normalize aux index. This percentage view helps us compare patterns across categories, even when sample sizes are different. Once the contingency table is created, we can look for patterns. In our example, all loan grades, A through G, show that the most common outcome is current. If every grade shows the same dominant outcome, this may indicate that there is no meaningful relationship between the two categorical variables. In other words, changes in loan grade do not correspond to clear, systematic change in loan status. Contingency tables are powerful tools to help us recognize whether categorical variables are related or whether they behave independently. Now, to try to explore the relationships between quantitative data and categorical data with box plots that can help us compare the distribution of a numeric variable across different categories. Box plots are powerful visual tools that allow us to quickly identify patterns, differences, and potential relationships between variables. A box plot makes it easy to compare how a numerical variable behaves across different groups. For example, consider flight delay data from the airline state table. We can use the box plot function with the by argument to create separate box plots for each airline. Here, we plot PCT underscore carrier underscore delay grouped by airline. The results are clear. Alaska Airlines shows the fewest delays, while American Airlines has the highest delay levels. The lower quartile of America is even above the upper quartile of Alaska, and this large gap indicates that delays are not evenly distributed across airlines. Therefore, a relationship likely exists between airline and the carrier delay percentage. If no relationship existed, the delay levels would be more similar across airlines. At last, we check about how to verify data quality. The task of verifying data quality involves examining the dataset to ensure its accuracy and completeness. So this includes determining whether the data covers all required cases and checking for errors or inconsistencies. It is also important to identify any missing values, understand how they are represented, locate where they occur, and assess how frequent they are. The output of this task is a data quality report that documents the findings. If any quality issues are discovered, the report should include possible solutions. Addressing data quality problems typically requires a deep understanding of both the dataset and the relevant business context to choose appropriate remedies. In data analysis, missing values occur when information for a variable or observation is not available. There are many reasons why this happens. People may skip questions in a long survey or choose not to answer sensitive topics. In experiments, equipment failure may cause data to be lost. If missing values are not handled properly, they can lead to biased results and incorrect conclusions. So before we continue with data preparation, it is important to identify missing values and understand where they come from. To begin, we check for missing values using the ISNO function in Python. When we apply order detail ISNO, it returns a data frame of true and false values. True means the value is missing. False means the value is present. To quickly see how many missing values each variable has, we use ISNO sum. For example, we may find that the variable order ID has one missing value. Next, to locate the exact rows that contain missing data, we add any axis equal to 1 after ISNO. This checks each row and returns true if any column in that row is missing. And this helps us find which record need attention before moving to data cleaning. There are several ways to handle or replace missing data. Removing rows with missing values is possible, but often wasteful, especially when the missing rate is high. The better approach is imputation. The first step is domain knowledge. We communicate with stakeholders to understand how the data was collected and whether the missing value can be recovered. For example, in the order detail dataset, if an order ID follows a sequence, stakeholders can confirm whether the correct value is 10295 or 10296. When true values cannot be recovered, we can use simple imputation methods, mean or trend. Imputation replaces missing values with the average. Median imputation works well for skewed data. Mode imputation is suitable for categorical variables. More advanced methods, such as k-nearest neighbors or regression imputation, also exist, but they are beyond the scope of this course. The goal is to choose an imputation method that maintains accuracy and keeps the dataset useful for analysis. Duplicate entries occur when the same observation is recorded more than once in a dataset. These duplicated rows can distort statistical results, especially totals, averages, and counts, because repeated records give certain observations more weight than they should have. To identify duplicates in Python, we use the duplicated method. It scans each row and checks whether it matches an earlier row. If it does, it marks that row as true. We can quickly find out how many duplicates exist by using a duplicated sum, which counts all rows labeled as duplicates. Once duplicates are identified, we can remove them using drop_duplicates, ensuring that only unique observations remain. This helps improve the accuracy, reliability, and validity of our data analysis. Outliers are data points that are very different from most of the observations in a DESD dataset. They can happen because of data entry mistakes, unusual events, or rare cases, extreme but real measurements. Outliers matter because they can skew statistical summaries like the mean and standard deviation and affect analysis and modeling results. A box plot is a simple visual tool to spot outliers. You can also use the interquartile range, or IQR, to detect them. The IQR method works like this. First, we calculate the first quartile, called Q1, by using the quantile function on the column quantity with 0.25. Then we calculate the third quartile, called Q3, using the quantile function with 0.75. The interquartile range, IQR, is simply Q3 minus Q1. To find the outliers, we select all rows where the quantity is less than Q1 minus 3 times IQR or greater than Q3 plus 3 times IQR. We can print these rows to see which values are considered outliers. Next, we will replace the outliers with more reasonable values. For example, in the order detail dataset, 2 outliers were found, 600 and 120. After checking with stakeholders, 120 was correct, 600 was a typo, and it was corrected to 60. To do this safely, we first create a copy of our dataset called order detail fixed. Then we replace the outlier value, for example 600, with the corrected value, 60, using the replace function on the quantity column. Finally, we check if the replacement was successful. We print all rows where quantity is still equal to 600, which should now return an empty set if the replacement worked. We can also check a specific row by using the order detail ID column, for example, the row with 44, to confirm that the quantity value has been correctly updated. Using this method, we can systematically identify extreme values in our dataset and correct them, ensuring that our analysis is more accurate and reliable. An overall data understanding report helps us make sure we understand the data before doing any analysis. It usually includes 3 parts: a data collection report, a data quality report, and a data exploration report. These sections explain where the data comes from, whether it is reliable, and what basic patterns it contains. The data quality report should be done first because poor quality data can lead to wrong conclusions. In this step, we check for missing values, duplicate records, and outliers, since these issues can distort results and analysis. After data quality is confirmed, the data exploration report examines quantitative data, categorical data, and relationships between variables such as quantitative versus quantitative, categorical versus categorical, and quantitative versus categorical. In the assignment practice, we will apply this process to a real case to show how data understanding works in practice.